Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action, a course in groups, rings, and fields. The subject of this lecture is showing that permutations of a set form a group. Before formally studying groups, defining them, and abstractly trying to see what we can say about groups, we would like to have a lot of examples. We want to see that these groups that we are going to study actually come up. In addition, we would like to have a set of examples so that we can hang our hats there, so that whenever we have a question, whenever we're talking about a theorem, we can think of examples. We can think of, okay, what happens in this group? What happens in that group? In a previous lecture, we talked about the dihedral group of order 8, the symmetries of a square, as one such example. This lecture will give us another set of examples to work with. The example that we really would like to work with is something called the symmetric group of degree n, Sn. And what that is permutations of a finite set. Take 1 through n and look at all their permutations, and they form a group. That will be the subject of the next video lecture. This lecture, I want to put this symmetric group, these permutations of a finite set, in a larger context. What we would like to look at is something called permutations of omega, where omega is just any set, finite or infinite. This perm omega will also be a group. That's what we will show today. And in fact, it can be an infinite group. If omega is an infinite set, it will be an infinite group. So what is permutation of omega? We'll go into much more detail in a moment, but it's all the functions from a set omega to omega. Omega is your favorite set, could be finite, could be infinite. And you look at all the functions where the domain is omega and the codomain is omega, and the function is a bijection. Bijection is another word for the function having the two properties of one-to-one and onto-ness. You could not worry about perm omega and go directly and just talk about the symmetric group. And for first-time readers, that's what you should probably do. But it's helpful to think about this more general context of one-to-one onto functions. If you're basically familiar with one-to-one onto functions, then all is going to be fine. I'm going to remind you of how we define a function and what's one-to-one and onto and so on here, but I won't prove all the theorems about it. For those, I actually have another set of videos for you that I would suggest you look. There's a video on one-to-one onto functions. There is another video on function composition, another one on invertibility. And actually, I have another video as part of the combinatorics set of videos on counting permutations of a set, in which we also talk about how permutations and one-to-one onto functions are one and the same. I would suggest watching those as a prerequisite for this lecture. Although you don't need to know all the details, X and Y are any set. I'm going to first tell you what bijections are, what one-to-one onto functions are. What's a function? A function or map, those are interchangeable words, from X to Y, X is the domain, Y is the codomain, is a rule that tells you how to go from X to Y. What it does is that it assigns to each element of X one element of Y. For every element of X, you need to have some element of Y that you map to, but only one element. So this is the way we think about it, that we've got X over here, Y over there, and F is sending things from X to Y. Every element here goes somewhere in Y. A function F is a rule for sending points of X to points of Y. If it happens that one point is actually going to multiple points, then you don't have a function. That's what the definition of function is requiring you not to do. You cannot send one element of X to multiple places. On the other hand, if you have two different elements ending up in the same place, that's okay as far as being a function, but then your function is not one-to-one. One-to-one means exactly that different points go to different places. And if there's some point delta in the codomain that's not hit by anything, if there is such a point that's just sitting there and nothing is being mapped to it, then the function is not onto. So for a function to be onto, everything in the codomain has to be the image of something. Something has to be sent to it. Omega is any set, possibly infinite, but maybe finite. If you don't like omega, you can call it X. I'm calling it omega because that's sort of a little bit more impressive. And permutations of omega are all the functions that have omega as the domain and the codomain. They don't go from X to Y. When I'm talking about functions in general, I will say things a little bit more generally, but for perm omega, and I will say in a moment why, the functions have to go from a set to itself, and they have to be one-to-one and onto. Again, another name for one-to-one and onto is bijection. Another name for one-to-one is injection. Another name for onto is surjection. And another name for one-to-one and onto is bijection. This is a set of functions, and it's our candidate for being a group. For a group, what you need is you need a set, and this is the set of elements, but you also need an operation that we usually call a multiplication, a way of combining elements of the set and getting another element of the set. And so we have to decide what that is for this set of functions. And for here, that operation is function composition, which I will talk about in just a moment. We also need that operation to have certain properties. So the whole project is to study sets with one operation where that operation has certain properties. That operation needs to be closed. That means that if you take two elements and combine them, multiply them, you need to stay within your set. The operation needs to be associative. So xy times z should be the same as x times yz. And there should be an identity, something that when you multiply, nothing happens. And every element needs to have an inverse. If you have an x, there got to be a y such that xy and yx are both 1, that identity. If you have those, then that's a group. And our project is to then study in some detail groups in the abstract. And when we say in the abstract, what we mean is that we are not going to worry about what the elements of the group are or what the operation are. We just are going to know that we have this abstract object. We'll try to see what we can say about it. However, in examples, it's not that abstract in the sense that we know what the elements are and what the operation is. Here, for example, the elements are bijections from a set to itself, and the operation is function composition. Let's talk about function composition for a second. I have a whole video on function composition where I go into much more detail, but the idea of a function composition is that you have a function from x to y. For f, the domain is x and the codomain is y. You have another function from y to z, g. For g, the domain is y and the codomain is z. And you want a function to go directly from x to z. And that function sometimes is called guff, g circle f. In group theory, we like to drop that circle and just call it gf, because we like to think of this as a product of g and f. We want to compose those functions and get another function. And what does it mean to get another function? That means that if you have some alpha in x, I need to tell you where it goes. Where does this function send that element alpha, which gamma it sends it to? The idea is pretty clear. Instead of going directly there, we'll use f and go over to y, and then use g, come down to z, and you'll end up somewhere. And that's where you're going to say your function gf is sending alpha. The function gf applied to alpha is the same as g of f of alpha. You apply f to alpha, then g to that, g of f of alpha. When we say gf, if these are functions, f goes first. The guy on the right goes first, then g. When we're in groups, we think of this as a product of g and f. But when you're thinking of this as a function, then you've got to know that f is going first. Omega is a set. F and g are both maps from omega to omega. Gf here is the name of the function. You apply it to x, what should you get? You get g of f of x. This is defining what gf is. Fg is also a function, but if you look at the diagram at the bottom, I switched the place of g and f. Then that function is defined by fg at x is f of g of x for every x in omega. Fg is another name for f circle g, and it's the composition of g and f. Again, g goes first and f goes second. In group theory, we really think of fg as the product of f and g. Fg, by the way, is not necessarily equal to gf. If you have two functions that do two different things, when you apply them in succession, you're not going to get necessarily the same thing if you switch the succession. If you try to cook an egg, if you break an egg and then fry it, it's very different than if you fry it, then break the egg. Those two operations are not going to commute. Why are we just talking about functions from omega to omega? If you want to use function composition, you have to have x and y be the same, because you can't compose a function going from x to y with another function going from x to y if x and y are different, because the codomain of the first function has to be the same as the domain of the second. And that's why we have functions from omega to omega. In group theory, one of the things we need is to have inverses. And as I will mention in a moment, there's a theorem that tells us only one-to-one onto functions have inverses. And for that reason, we can't just look at all functions from omega to omega. We need to look at permutations of omega, what I call perm omega. Some other people call that S sum of omega or sim omega, symmetries of omega. Perm omega is the functions from omega to omega that are one-to-one and onto. But there's a subtle point that comes up. The set of functions from omega to omega are closed under function composition. If you take two of them and compose them, you get another function. But now that we have put extra conditions and we're requiring our functions to be one-to-one and onto, you have to make sure that if you compose one-to-one and onto functions, then you still get a one-to-one onto function. And also that the inverse of a one-to-one onto function is a one-to-one onto function so that you stay within this set perm omega. In fact, there's a theorem, and in the video that I have on function composition, I go through a complete proof of this. Although it's not very difficult, you could try to prove this yourself. If you have a function not just from omega to omega, if you have a function from x to y and you have another function from y to z, then you have an irresistible urge to compose them and find the function gf that goes from x to z. If f and g are one-to-one, then gf is also one-to-one. That's a theorem that needs a proof. Again, the proof is not too difficult. It does appear in my video on function compositions. If f and g are onto, then gf is onto. And because of that, if f and g are one-to-one onto or bijections, then gf is also a bijection. This says if you have fg in perm omega is one-to-one onto functions from omega to omega, and if you compose them, you get something in perm omega. This is what closure means. I have an operation, and when I operate, I stay within my set. So it's closed under function composition. For a group, we need four properties. We need closure, associativity, identity, and inverses. Not that much. The group doesn't ask for much, but it does ask for those things. Perm omega is closed under function composition. It's also associative. If you do f times gh, or if you do fg times h, I claim those are the same. How would I know if they're the same or not? Well, I've got to apply them to an element, see if they send them to the same place or not. Whether or not you do fgh applied to x or fgh applied to x, at the end of the day, what you're going to get is f of g of h of x. You have to write down a line or two, but that's associativity. Now let's go to identity. If omega is an arbitrary set, then the map that sends any element to itself is called the identity map. Identity is the map that doesn't really do anything. It just sends everything to itself. It's basically doing nothing. But it's really important in the context of group theory because you need to have an identity. If f is a permutation, an element of perm omega, then f times 1 omega, find the composition of 1 and f. Do 1, do nothing, then do f. Well, that's the same as doing f. And the same the other way around. If you do f first and then nothing, that's the same as having done f. And so this identity map is the identity. The only thing left is inverses. Let's talk about what inverses are. If you have a function from x to y, then some other function g that goes the other way from y to x. So for f, the domain is x, the codomain is y. For g, the domain is y, the codomain is x. F and g are inverses of each other. If whenever you follow one by the other, you're back where you started. That's the intuitive way of seeing it, and I'll write down in a second the formal definition. That means that if you start with alpha here and use f to go over there, and maybe it goes to beta, then if you apply g to beta, you need to be back at alpha. It also says that if you start with beta and apply g and get alpha, then if you apply f to it, you need to go back. Regardless of where you start in x or y, and you apply one of these functions, the other function has to undoes what you did and get you back where you started. If I want to write it formally, if x and y are set and f is a map from x to y, then a map from y to x is the inverse of f. If g of f of x equals x for all x in x, and f of g of y is y for all y in y. Such a g is denoted by f inverse. F inverse is just another name for this function. To remind you that that function is the inverse of this other function that you were talking about, you call that f inverse. You give it a new name. Someone might have a name Mark, but I might want to call it my best friend. That doesn't mean that they're not called Mark anymore, but they are also my best friend. If f and g are inverses of each other, another way of saying the same thing is that gf is the identity on x and fg is the identity on y, because identity was the map that sends everything to itself, and gf is the map that you do f and then g. So another way of saying that you have an inverse is to say that the product gf and fg is identity. By the way, this whole definition you can define using this diagram. Here I have x and y. These are the sets x and y, the function f. then the function G, the function F, the identity function, and the identity function. What's the point? In algebra, we a lot of times like to say things in terms of commutative diagrams. So this diagram is a commutative diagram if and only if F and G are inverses of each other. What's a commutative diagram? A commutative diagram is a diagram that if you start at any node and go to another node via the arrows that you see, you might be able to go from one place to another 2 different paths. If it doesn't matter which path you go and you always end up in the same place, that's called a commuting diagram. Here, for this to be a commuting diagram, doing this F and then G has to be the same as doing identity map on X. And also doing G and then F should be the same as the identity on Y. So for this set of sets and maps to commute, F and G have to be inverses of each other. So a fancier way, if you want to impress your friends, way of saying that F and G are inverses of each other is to say that F and G are inverses of each other if and only if the following diagram commutes. Lots of things in algebra can be turned into commuting diagrams. One thing that's important for us is the following theorem, for which there's a complete proof in my video on inverses. If you have a function from X to Y, you might wonder, when does it have an inverse? It has an inverse if and only if it's 1-to-1 and onto, if and only if it's a bijection. And again, I'm not going to go through the proof of that here, but I have a complete proof on a video on inverses of functions, where examples are given and the theorem is proved. Corollary to that is that if F is a 1-to-1 onto map, then F inverse is also 1-to-1 onto. Why does that follow? If you have a 1-to-1 onto map, then first of all, it'll have an inverse because it's 1-to-1 and onto. Why will that inverse be 1-to-1 and onto? Because that inverse has an inverse. What is that? That's the original map. That theorem tells us that this F that was 1-to-1 and onto has an inverse, but because the inverse of the inverse is the original function, that inverse is also 1-to-1 and onto, because that theorem was if and only if. If F is a permutation, then it's bijective and therefore it has an inverse. And not only that, F inverse is in Perm omega. We now know that Perm omega is a group. Again, we haven't started formally studying groups, but we're looking at examples. And so here's an example, and you should compare this to the symmetries of a square. We have a set called Perm omega. And what is it? In this case, in the case of examples, we know what the elements are. They're bijections, 1-to-1 onto maps from omega to omega. For every 2 elements, we have defined the function composition. So Fg is the composition of G and F. Gf is also the composition of F and G. And we know the following properties. First of all, if F and G is permutation, then so is Fg. If FGH are permutations, then FGH is the same as FGH. So the closure and associativity. And we have an identity. We have this function 1 omega, the identity function, that when you multiply it by other elements, nothing happens. Again, when I say multiply, I have defined what the multiplication is, and that's function composition. And every function in Perm omega has an inverse that's also in Perm omega. So this guy is a group. This is what a group means. One particular case of this, the subject of the next video, is when omega is a finite set. Our go-to set with n elements is the set 1 through n. 1-to-1 onto maps from 1 through n, 1, 2, 3, 4, n, to itself are called Sn, or the symmetric group of degree n. So this is the end of this lecture. This is a part of a series of lectures on abstract algebra. Before this, there was the general talk about what abstract algebra was, then the dihedral group. This was permutations. The next one is symmetric group. And then it's a short video showing that S4 has a subgroup isomorphic to D8. Till next.